Today's lesson, we will be covering Gibbs free energy. Gibbs free energy is named after Josiah Willard Gibbs. He was a physicist and chemist in the late 1800s. Gibbs free energy, or G, is a measure of spontaneity. So the symbol that we use for Gibbs free energy is G, and we talked about entropy being S and enthalpy being H. So this is the symbol for Gibbs free energy. And it, like I said, a measure of spontaneity of a reaction, and it's based on the release of free energy. And we could say free energy is energy to do work, or it's available energy. So that's what the free part of free energy means. And just like there's several ways to calculate enthalpy or entropy, there's also a couple ways to calculate delta G. And we'll discuss those calculations later in the video. So you can see on this slide that I have a couple statements that are very important about delta G and the sign of delta G, whether a reaction will be spontaneous or non-spontaneous based on the sign of delta G. So if delta G is less than 0 or negative, then the reaction will be spontaneous. So if the reaction is spontaneous, that means it releases free energy, and it's what we call an exergonic reaction. Exergonic is a new term that you have not seen before, and all that means is that a reaction releases free energy. You could almost think of it like the term exothermic, where it's releasing heat into the surroundings. Exergonic is releasing free energy in a reaction. So when delta G is 0, it's spontaneous reaction and it's releasing free energy. When delta G is greater than 0, or a positive value, we call this endergonic, and endergonic means that it requires energy. Just like an endothermic reaction is going to absorb heat into the system, endergonic is going to require energy to be absorbed into the system for the reaction to proceed. So we would call this a non-spontaneous reaction. So delta G that is positive is going to be non-spontaneous. And if delta G is at 0, that means it's at equilibrium. And times where delta G will be 0 would be if something is melting and it's at its melting point, or if something is boiling or vaporizing and it's at its boiling point. Those would be times where delta G would be at equilibrium. So those are just some good examples if you want to add those to your notes. So there's two main ways and equations that are used to calculate delta G. One way is taking the sum of the delta G's of formation of the products and subtracting the delta G's of formation of the reactant. So again, something very, very similar to what you've already seen before. So nothing different there. You're going to look up those values in Appendix 4 in the back of your book. Sorry, my handwriting's a little bad today. And again, these are at standard states. That's why we have that little degree symbol there. So that is one way that we can calculate. Another way that we can calculate delta G is by using enthalpy and entropy values, or delta H and delta S values, and the temperature. The temperature has to be in Kelvin, and you have to make sure that all of your units agree. So delta H is usually given to you in kilojoules, and delta S is usually given to you in joules per K. So you're going to want to either change the delta H to joules or the delta S to kilojoules. And I usually change the delta S to kilojoules because delta G is usually given to us in kilojoules. So that just kind of keeps everything in line with the way things are reported for delta G in your textbook. One other important thing to say about delta G is that it's a state function, just like delta H is a state function, just like delta S is a state function. It doesn't matter how you get to the final values for enthalpy and entropy. It doesn't matter how you get to that goal. You still get the same result when you get there. And I did talk to you about state functions before in terms of, I think the analogy I used was climbing a mountain. Maybe you're the type of person that's going to just go right straight up the mountain, but maybe your friend is going to want to take a longer path to get there and go back and forth across the side of the mountain to finally get to the top. You're both getting to the top of the mountain, but you went in different ways, but the goal was still the same. And that's the same with delta H and delta S and also delta G. No matter which one of these equations that I use, I'm still going to get the same value for delta G. So I wanted to just make that clarification. The only time that the delta H minus T delta S would be different is there you have a temperature that's integrated into that equation. And so if that temperature is not room temperature or 298 K, then the delta G is going to be different than if you used the standard states, because that standard state, that's 298 K in 1 atmosphere. So that's when delta G's would be different. But for the most part, your delta G's, you're going to get the same result at the same temperature, at that state, at that standard temperature of 298 K. Now the next several slides are going to cover a lot of the sample calculations for delta G that are in your textbook. So the problems in some cases may have several steps, so bear with me as we proceed. Make sure you have your calculator handy as I go through all of the examples. So I apologize if this PowerPoint video gets a little bit long, but I want to make sure that you have enough examples to help you with your homework that you're going to have due on the weekend. So here's the first example. We're looking at the reaction of sulfur dioxide and oxygen gas to give us sulfur trioxide. It tells us it's being carried out at 25 degrees C and 1 atm, and we're asked to calculate enthalpy, entropy, and Gibbs free energy. So we're calculating three things. You can see that I have at the bottom of the page the heats of formation and the entropy values at standard state. We can use these to calculate H and S and then calculate delta G using those two values. This is done at room temperature, so 25 degrees C, which is going to mean 298 K when we get to using this at for delta G. So I went ahead and wrote out the work for delta H, and I came up with a negative 198 kilojoules. And that means it's exothermic. It also means it's a favorable reaction because it is exothermic. And I went ahead and calculated delta S at standard state, and I have a negative 187 joules per Kelvin. Again, I want you to make sure that you are looking at those units, because I am going to have to convert that to kilojoules. And to convert that to kilojoules, I'm going to divide by 1,000. So I end up with negative 0.187 kilojoules per K, because I'm going to use that next. Now, the delta S is negative, so that's going to be unfavorable. I don't have room to write that in there, but that's going to be unfavorable. Anytime that there's a negative delta S, it means less disorder, so it's unfavorable. This makes sense because if you look back up at the reaction, I have 3 moles of gas on this side and 2 moles of gas on this side, and so I decrease the amount of gas molecules in that reaction. So even just looking at the reaction, I can predict that delta S is going to be negative. Now the last thing I want to do is calculate delta G. And because this is at 25 degrees C, and I calculated delta H and delta S at 25 degrees C, I can use this equation for delta G, the delta H minus T delta S, and I can plug in what I know and solve to see if this is spontaneous or exergonic. So here I've done the work for you for calculating delta G, and you can see that I ended up getting a negative 142 kilojoules for delta G. That is less than 0, so this reaction would be spontaneous, or we could also say exergonic. Those kind of words can be used synonymous with each other. Now we can also calculate delta G if we're given reactions that occur and we have the delta G's that go with those reactions, we can kind of do it like the Hess's law, the summation that we did, reversing, multiplying by 2, whatever we do to delta H, whatever we did to the reaction, we have to do to delta H. It's the same way with delta G. If I reverse something, I change the sign. If I multiply through by a integer, I have to multiply the delta G by that as well. So this reaction is just really quick to kind of refresh your memory on how that is done. So for this one, we have carbon as a diamond forming CO2 gas, and carbon as a graphite reacting with oxygen and forming CO2 gas. The overall reaction, though, is diamond to graphite. So I need to reverse the equation B. So B is going to get reversed, and that's the only thing that I need to do is reverse that reaction. And when I reverse that reaction, it gets rid of the O2 and it gets rid of the CO2, and I'm left with carbon diamond to carbon graphite. And so this sign needs to change for the second reaction, and delta G ends up, you just add together just like you did for delta H, and you get -3 kilojoules for this reaction. Now delta G is negative, which means it is spontaneous, but I've said this before, if this were a spontaneous quick reaction, we wouldn't have diamond jewelry, that stone in any of our jewelry, because it would turn to graphite and it would be black and yucky. So this is something that occurs over a very, very long time. So even though it's spontaneous, it's one of those reactions that does take a really long time. So again, we can use the summation of the delta G's to calculate the overall delta G of a reaction, very similar to doing that with delta H. So that's the second example. And sometimes chemists want to determine if reactions are going to actually be feasible to make something. So this sample problem says a chemical engineer wants to determine the feasibility of making ethanol. So he wants to make ethanol, or she, by reacting water with ethylene, C2H4. So they want to know if this reaction is spontaneous under standard conditions. So standard conditions we know are 298 K and 1 atmosphere. So those are our standard conditions. And you'll notice down here I have the delta G values already written out for you, but you could look them up in the back of your textbook in Appendix 4 to find them. I just wanted to make it a little bit simpler, since I know you know how to use that table already to calculate delta G. So I went ahead and I calculated this for you, so you can see that I wrote in the values that I needed for each of the compounds that were involved in this reaction, and then I took the products and wrote them and subtracted the reactants, adding those two together and then subtracting from the -175, and I got -6 kilojoules. It's a negative value, so it's spontaneous. Delta G is less than 0. Now, a chemist may also want to consider other data, not just at standard conditions. Especially, they may want to change the temperature to see if that increases the amount of product that would be formed, and if it would also stay spontaneous. We only looked at room temperature, but they might want to consider taking temperature into account and increasing the temperature and seeing if the reaction is still spontaneous at that temperature, and seeing if more product is formed. So that's the whole point of looking at all of this data, is to determine for a scientist the feasibility of maybe preparing something that they might want to sell, or they might want to use for another application where they are working. Now the example here is a vaporization process. It's a phase change. We're going from a liquid to a gas, so bromine liquid to bromine gas. And this would be spontaneous at all temperatures, and because this is a vaporization or phase change, delta G is going to be, we're going to be setting delta G to 0, and rearranging the equation to solve for T. So I've gone ahead and I've set the delta G to 0, and now I want to solve for T. So what I'm going to do is add T delta S to both sides. So I'm going to get T delta S on this side equal to delta H, and I want T by itself because I want to solve, the question was asking what's the normal boiling point of liquid bromine. And so in order to solve for that, given H and S, I could solve for T because I know H and I know S. So T is going to equal delta H over delta S. So I'm going to use that equation, plug in what I know, and solve. So because this is at equilibrium, the temperature of the liquid and the gas, I should say, are at equilibrium. So that's why I can say that delta G equals 0, and I can solve for temperature. And this temperature would be the boiling point. So the temperature at which the liquid bromine will boil is at 333 Kelvin. And again, I converted the 93 joules per K mole to 0.0930 kilojoules per mole per K, so that my units would cancel and I would end up with Kelvin as my final unit. So determining boiling point or determining melting point means that delta G is at 0. It's either the solid and the liquid or the liquid and the gas are at equilibrium. And if you need to find what the boiling or melting point is, you can set G to 0 and solve for the temperature. So that's how you would work out those particular problems. Obviously, you need to be given enthalpy and entropy, so you could plug in and solve for temperature. Now the next set of slides, I'm going to focus on the delta G equation using enthalpy and entropy, and how we can use what we know about entropy and enthalpy to make predictions on spontaneity. So the first example, probably the easiest example, when delta H is negative, we know that it's going to be a spontaneous reaction. That means it's exothermic and it's favored. And when delta S is positive, we know that more disorder has increased in that reaction, and we know that that is going to be a spontaneous reaction as well. So if both of these are favored, then delta G will always be negative. So no matter what temperature you put in there, if the delta H is negative and the delta S is positive, it's going to be spontaneous at all temperatures. So that's probably the easiest one to remember. And this one is pretty easy to remember too. If delta H is positive, it means it's endothermic and it's not going to be favored. So this would not be favored because it's endothermic. I put delta G there, that should be an S. Whoops, let me fix that. If delta S is negative, that means that the disorder has increased, and so that's not favored, non-spontaneous. So if both delta H and delta S have signs that are saying that that it's non-spontaneous or unfavorable, then no matter what the temperature is, it can never be spontaneous. So delta G will always be positive. So delta G will always be positive in this scenario, and that means that it will always be non-spontaneous when H is positive and entropy is negative. Now here we have a delta H that's going to be positive, and here we have a delta S that's going to be positive. So here I have a scenario where I have entropy being favorable and I have entropy being unfavorable. So there's only one way that this can be spontaneous, or only one way where delta G can be negative. And so that means the magnitude or the size of the T delta S has to be greater than the delta H. Because what is happening here is you end up having a positive delta H, which then you're going to subtract from something that is also going to be positive. And so in order for delta G to be negative, this term, the T delta S, has to be greater than the delta H. So that's the only time that magnitude of the temperature times entropy has to be greater than delta H in order for delta G to be negative. In our last scenario, we're saying delta H is negative and delta S is negative. And so this can only be spontaneous when T delta S, the magnitude of that, is less than the delta H value. And again, if I start to plug numbers in there, you can see it a little bit better. But anytime that I have this negative and this negative here, that's going to end up being positive when I go to do that math. So in order for delta G to be negative, the positive T delta S must be anything less than whatever the H value is. Like for instance, if I say delta H is 50 kilojoules, then the T delta S has to be anything less than 50, because that's the only way that the delta H would be negative and spontaneous. I hope that makes sense. So that's the last scenario where we have delta H and delta S both being negative. Okay, the last thing I have to show you is your assignment. So there's some textbook problems. I moved some problems around this week, so just as long as you get them all into the Dropbox and I can see them all there, you'll get credit, because I kind of realized I gave you some problems that I said were due earlier in the week, and they really should have been given with this assignment. So if you did things out of order, it's okay. As long as you have all of them done, you'll get credit. So page 784, you're going to work on 27 to 31. You can submit a picture or PDF to the Dropbox to submit that, and it's due on Sunday, April 26th. And just a heads up, I believe towards the end of next week, we are going to have an assessment on Chapter 16. So it will just be covering Chapter 16. And when I put the lesson plans up, I'll make sure I put the objectives in there so that you can see which objectives it is off of the objective sheet. All right, so that is our lesson on Gibbs free energy. Remember, it's energy that is available energy from a reaction. And again, several ways that you can calculate that delta G, which I showed you today in this lesson. All right, guys, see you next time.